to have 6 talks that will last 10 minutes each. And first of all, we'll be hearing from Enrique Borja, PhD in physics. His PhD thesis was about black holes. He's also a script writer in the Spanish TV show Orbita Laica. He will be talking to us about things that we don't know about.
Hola, muy buenas tardes.
Good evening. I'm very happy to be here. This is my second time in Passion for Knowledge. And since I'm getting old, I'm not going to talk about science a lot. I'm going to talk about philosophy, or about how I see the world lately. And I would like to say, first of all, that science is that based on our ignorance. I mean, science is an accumulation of questions we don't know the answers to. Right. Let's see if my PowerPoint presentation works. So this is the first question we need to answer.
Perdón, esto no. ¿Hay algún sitio aquí? Bueno.
So, the pleasure of not understanding.
Bueno, pues este es el título de la charla.
This is the title of my talk. And here we could talk about so many different things, like for instance the origin of life. There are a number of different things in chemistry that we don't know about. I am a physicist myself. Then later on you'll have a mathematician. Things will get worse and worse. I'm going to focus on physics and on 2 aspects of physics. First of all, quantum physics, of course. Quantum physics that is like 130 years old now. Incredible things have been achieved. We're about to have quantum computers that will change the way we understand computing and the way that calculations can be made to solve actual problems. For instance, to design new antibiotics. We have a huge problem with superbacteria. That's a huge issue we need to face. That's a challenge for us. It's going to be relatively simple to make calculations thanks to quantum computing. On the other hand, we have no idea how quantum science works, and that is incredible. And what surprises me most is that they always started studying light bulbs, which seems very simple, right? Not LED or LED light bulbs, but the traditional ones with filaments. This is a thermodynamic system, and people would wonder, how can this emit energy? Well, you see that the energy that is emitted by light bulbs is basically made of magnetic waves with a specific length wave. So a hot object emits a specific amount of energy per wavelength. And that's what we studied back in time in laboratories, and the curves were measured. That's what you see here. We would get, depending on the temperature of the filament, we would get one curve or the other. These are, of course, ideal curves. And this curve will tell us a lot about the nature of that, of what was going on. If we took our best theories up to that time, they would foresee that for these, for short wavelengths, any hot object should or would burn and explode. Well, that was a conceptual crisis for us. How could that be possible? And then we have the mythology of physics, and Max Planck in the 1900s suggested that energy behaved in a specific way. That was a headway in the way we understand nature, and this has led us to accepting that things can be both in 2 places simultaneously and can be interrelated very closely. So if I have 2 objects that are intertwined in a quantum way, they are still part of the same system. If I touch something here, it would be felt over there. And that is incredible, isn't it? Another question is, why is that happening and how? And the answer is, we don't know. In fact, there are so many conferences, meetings, about that. We've been working on that and trying to answer that question for 100 years, and we don't know. And I don't think that, I don't think that I'll be able to see this in my lifetime, as Jocelyn would say. And it's incredible because, remember, we started studying light bulbs, so we're going to end up making quantum computers, and we don't know a thing about theory. It makes us humble, right? The universe is making us humble. You're doing things and you don't really know what you're doing. It's like driving with your eyes closed. But there are good things about it. For instance, we understand matter better as a deep level. I mean, we can understand why atoms are stable. And not just that. We can see how the atoms are made. The atoms that are within protons and neutrons, like we have particles like quarks, leptons, and other cosons like and other particles like bosons that transmit interactions, electromagnetic interaction, strong, weak interaction. And then we have this friend over here, which is the Higgs boson, that proves that there is a mechanism explaining the origin of the mass of the rest of the particles, more or less. But we have a problem here, and that particle that was postulated back in the 60s was discovered in 2012 on the LHC. The problem is that we discovered it, and our theories said that it would have a mass range around 120, 130 giga-electron volts. Those are the kilos of particles, and we were right. That particle has a mass of 125 mega-electron volt, more or less, according to what the official data tell us. And that is a problem because a best possible theory based on quantum theory says that that particle should be thousands of times heavier. And what happens here? We just measured something that has this mass, this value, right? But what surprises us is why the value is so low. It should be thousands of times greater. So we are looking at how matter is formed. We've come to the building blocks, and then when we wonder why things have mass, we need to go to the Higgs boson. And as it turns out, we don't understand why its mass is what it is, right? So hypotheses are made here, like all the particles need to have some colleagues, which we don't see, and we say, okay, don't worry. In the next accelerators, if we increase the energy of collisions, we will see them. Problem is, we haven't seen them. We've been working with HLC for a long time. We expected to see these supersymmetric particles, and we don't see them. That's a problem because we cannot explain a great deal of the physics that is around us, and this is a crisis. But there's another crisis that's even more interesting to me. We learned to look at the universe, and in the universe, this is Wilson Mountain, and in 1929 it was found that galaxies are expanding. This is a very famous chart. We saw this straight line, and someone said, Edwin Hubble said, the universe is expanding, right? If a student shows this chart and says that, they will fail. Because with 20 elements, you cannot say that the universe is expanding. He took a risk, and he was right. Everybody congratulated him on that. But what's funny is that with the current measurements, we know that the universe is expanding, all right? All the galaxies are expanding, and they do it with a specific acceleration, so the speed is increasing. And now, this leads us to this parameter in cosmology, which is Hubble's parameter, that is related to the expansion, the speed of the expansion of the universe. So we have a measurement of the age of the universe, and what happens here, we can measure the expansion of the universe looking at galaxies and looking at the light we get from there. If it is reddish or bluish, we know we can measure that speed by looking at how the galaxies are further and further away from us. And we do this better and better. We make less and less mistakes here. But we can also do this by looking at the light that we get from or every corner from the universe. That's the background radiation, and we're measuring this better and better every day. And what happens here? Well, I have two very good methodologies to measure the expansion of the universe or the age of the universe. And as it turns out, each one of the methodologies gives us a different value. So, with our best methodologies, we look at the universe, we ask them, how old are you, or how are you expanding? And we get two answers. And we don't know why. We don't know why we're getting two answers. And this is wonderful. Why? Because the universe is expanding, because something makes it expand, and that something is dark energy. What is it all about? We don't know. We simply named something that we don't know about. We don't know anything about. And I like this picture because let's not forget that this is something that some monkeys have achieved. Some monkeys that lost their hair and learned how to use stones and sticks. And now they're wondering what's their role they need to play in the universe. Thank you very much.